All right, good day, everyone. Welcome to our YouTube lessons on stoichiometry. Um, Today we'll be looking at this aspect of stoichiometry that has to do with the stoichiometry of solution. This is the stoichiometry 3 video. Now, the stoichiometry 1 and 2 video has to do with the relationship, the mass to mass, the mole to mole relationship, and that's for stoichiometry 1, while stoichiometry 2 has to do with percentage yield, limiting reagent, actual yield, then calculating mass and mole of excess reactant. Okay, for this stoichiometry 3, we have to do with the stoichiometry of solutions, where I have to look at molarity, molality, normality, mole fraction, and mass percent. So those are the key highlights of this video. So just stay tuned, and before we move further, don't forget to subscribe. If this video at the end of the day I know it will be useful to you, subscribe, hit the notification button, share to your friends and classmates that will also need it. Now, stoichiometry 3 video, stoichiometry of solutions. So I'll quickly throw light on explain the meaning of these terms, then start solving questions with some of my formulas and some of my key. Now, for molarity, molarity is the number of moles of solute per volume of solution. Per volume of solution. So number of moles of solute per volume of solution is molarity, and the unit is mole per dm cube. So they can also express molarity like this. You see, for instance, a question will take 0.5 capital letter M. This is 0.5 molar. So it means molar concentration or molarity of H2SO4. So it means 0.5 mole per dm cube of H2SO4. That is, in the solution, there are 0.5 mole of H2SO4 per the volume per liter of solution. So there are 0.5 mole of H2SO4 per liter. So that's why the unit is mole per dm cube or mole per liters. Dm cube is liters. Now, for molality, molality is the number of moles of solute per mass in kilogram of solvent. Yes, so molarity is so the unit should be mole per kg. So mole per kilogram, per 1 kilogram, number of moles per 1 kilogram of solvent. That's molality, and it should not be I see some expression going on online that has to say molarity is molality is molarity over density, or no, or molarity is density over molarity. So such expressions cannot work because molarity is per volume of solution, molality is per mass of solvent. So the relationship between molarity and molality has to be extreme and explanatory. Though we'll look at that in the later course of this video. So this is for molarity, this is for molality. So what about normality? Though normality is a unit of concentration no longer in use as of today, it is no longer in use, and it has been said to be to be um to be dropped or extincted, if I use the word. So we can't get terms like 0.5 normal. Okay, but let me quickly talk just throw small light on molality. Now molality can also be written as, for instance, for this H2SO4 now, I change it to 0.5 small letter m. So if it is small letter m, 0.5, this is not molar, this is molar. So 0.5 molar. So this is 0.5 molar of H2SO4. That means there's 0.5 mole of H2SO4 per kilogram of the solvent. All right. Quickly for normality, normality is the number of equivalent of solvent, per liter of solution, or we say per volume of solution. So number of equivalent of solvent per volume of solution. That's for normality. And in the later course of this video, I'll tell you how to get the number of equivalent, and try to get the number of equivalent, how you can get it from equivalent rate, and so on and so forth. Now, let me just quickly introduce mole fraction. Mole fraction is the fraction of the moles of a solute or a solvent in a mixture. Simple. So mole fraction usually represented with the symbol X. It has no unit. So for instance, I have a mixture of A and B, and it happens that A is the solvent and B is the solute. The mole fraction of B is going to be the number of moles of B all over the number of moles of A plus the number of moles of B. As simple as that. So the number of moles of one of the solutes over the total number of moles of the constituent of the solution. That's the mole fraction of that particular solute. Now, for mass percent, or what we call weight percent, or what we call weight in weight percent, we call it mass percent. I like to represent it with the symbol P. So in my subsequent solutions or subsequent solving, I'm going to represent it with the symbol. I'm going to represent it with the symbol P. So it is weight in weight solution, weight in weight solution, weight in weight. So weight in weight or percentage weight. Now, what does percentage weight stands for? Percentage weight, some people call it percentage P, W in W. So you might see it like this. You might see it. If you don't see it as P, you say a H2SO4 makes up 20% W in W solution. So this means weight in weight percent. So mass percent is actually the mass of a solute. So mass of solute all over mass of solution, all over mass of solution, that is solute plus solvent times 100 over 1. That's weight to weight percent. So I'm going to relate all these, parameters later on in this video as we solve questions. So I'll go for simple molarity questions, and this first one goes like this. All right, diving into the first question, it says calculate the molarity of a 0.5 grams of NaOH in a 200 cm cube solution. Very simple. I'll give you my first formula for molarity. So for molarity, at first, use this expression to always solve. Now, for molarity, remember it's number of moles over volume of solution. So we're going to use mass of solute over the molar mass. I'll represent molar mass as W times 1000 over volume. Now this your volume should be in cm cube or in milliliters. So when the volume is in cm cube or milliliters, we solve molarity like this. What can then be molarity? Molarity, mass 0.5. Now we need molecular weight of sodium hydroxide. Obviously, that sodium hydroxide does not have molecular weight. It's a formula unit, so it has a formula mass, formula weight. So the formula weight of NaOH is going to be 23 plus they give us Cl, we don't need Cl. So Na is 23, O is 16, and H is 1. So we should have 23 plus 17, that should be 40. We want to have 23 plus 70, 40. So the molecular mass or the molar mass or the formula weight is 40 times 1000. Our volume is in cm3, so this formula is valid. So we say 200. So as simple as it look, what will be the molarity? What will be the molarity of 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 um, of the solution? The molarity of the solution using my calculator would give me 0.5 times 1000, that's 500, divided by 40 divided by 200. So the molarity should be 0.0625. So 0.0625 molar, or we say mole per dm cube. That's for solution one. So simple. So simple. Very simple. Very simple. So we saw other ones. So let's quickly dive into question two, solution two, still on molarity. All right, question two says calculate the molarity of a 20% weight in weight. I think I explained what this thing means. This is mass percent or percentage weight or percentage composition of H2SO4 solution with a density of 1.195 gram per ml. Now, there is a long process of solving this question. Due to time and sufficiency and effectiveness for this video, there's a way, because I have density of solution, I have the percentage of solution. I could have used the long method to bring out the mass of the solute here and find a way to get the volume of the solution from this density. But all those are not needed. They will not be needed at this moment. I just have a short formula. So now, if you look at the first example, they gave you mass. Anytime they give you mass and volume, That was that one. You can calculate molarity for that first example. Now, this other example is when they give you density, they give you percentage composition. So we're going to look at tougher examples as time goes. Tougher examples, very tough examples. So, but for this kind of molarity question, calculate the molarity of a 20% H2SO4 solution with density. So after all said and done, I derived the formula to quickly solve this kind of question when they have percentage composition and density. Now, deriving the formula, for those of us that will need derivation of the formula, if you just request it, you can DM me personally, just say it on the comment section, and I'll send you the solution. Or subsequently, if you want, you request it as a video, I'll do it here on YouTube with time. So how to connect molarity with percentage composition and density, how the formula came about. So the formula I derived was 10 times percentage composition, or 10 times percentage weight, times density in gram per milliliters, not density in gram per liters, all over molecular mass or molar mass. This is the formula that connects molarity, percentage composition, and density. Now, it should be noted that there is also a unit of, or there's also a concentration of solution that we refer to as volume in volume percent. In as we have weight in weight percent, we have volume in volume percent. Now, we also have volume in weight percent or weight in volume percent. So those are all unit of concentration, or they are all ways to measure concentration: molarity, molality, normality, weight in weight percent, volume in volume percent, weight in volume percent. So they are all needed, even in um, concentration in parts per millions. So they're all parts per thousands. So, but the common ones we'll look at for this video as we continue our first year examination in the university. So, for this one, it's quite simple. I already have an answer. So, very simple. So, I can say quickly that molarity is equal to 10 times what's P? P percentage is 20, done the work for you, times density is 1.195, all over the molar mass of H2SO4 is 98. So use your calculator. H is 1, you can do that. X is 32, that's the molar mass, and O is 16. You can do for H2SO4, you get 98. So let me quickly use my calculator to do this for you. Using my calculator to do this, and I should have 10 times 20 times 1.195, that's 239 divided by 98. Should have 2.4 molar. So I have the 2.43, 2.44, pardon, 2.44 molar, 2.44 mole per dm cube. So this is how to calculate molarity for percentage composition. The third example on molarity will be a way to calculate molarity for molality. So I'm going to quickly work on molality now and show you how to relate their two. And I'll give you a general formula that can do that. So example 3. So just watch this. All right. This example 3 goes like this, and it's quite simple. It says, what is the molality of a solution of 1.55 molar? Now, 1.55 molar H2SO4 solution. Now, this big letter M, I already said it means molar, mole per dm cube. If it was 1.55 small letter m, this would be molar. This would be molar, like molar. But 1.55 big letter m is molar. Molar, so mole per dm cube, mole per kilogram. So those are the units of the of those two solutions. All right. So having having noted that, I will now attempt the question. Now, having a density of this. Now, they're asking us to calculate molality from molarity. Molality from molarity. Molarity was given, they asked us to calculate for molality. So very, very simple. Very, very simple. Is what I can quickly do. What I will do. Now, how do you do this? How do you do this? Now, if you watched the video earlier, we said molarity. Let me just analyze the question so you see it. If you watched, yes, I said earlier that molarity is number of moles of solute over volume of solution. Okay, now while molality is number of moles of solute over mass of solvent. So you are seeing that there are two different things. Mass of solvent, kilogram of solvent, cm cube or dm cube of solution. So there are two different units, but we can connect them. This is my simple way of connecting them, my very simple way of connecting them. Though they have a formula that I can use to connect them, but I will not drop that formula in this video. But I can connect them. How do I connect them? Now, first, I will try to get the percentage composition. That is the weight in weight percent. The weight in weight percent of the solute in the solution. Once I can get the weight in weight percent from the formula I gave, I remember I gave a formula that says molarity is equals to 10 times P times D all over molar mass. Molar mass was given all over molar mass. So I will try to get the percentage composition of the solute in the solution. Then, because I already have molarity, then once I get the percentage composition, from the percentage composition, I can go and calculate for molality. Now, it should be noted that this standard formula for molality should be noted. Every person watching this video should know this formula for molality. What did the formula say? The formula says that molality is equal to mass of solute over molar mass of solute times 1000 over mass of solvent in grams. Now, this is the formula for molality. Yes, this formula for molality should be noted by everyone. Everyone should know this formula for molality. So what I need for molality is mass of solute and mass of solvent. Mass of solute, mass of solvent. Remember, W is the molar mass of the solute, H2SO4. So this is H2SO4 solution. So H2SO4 and we have the solvent. I need the mass of the solvent, just the mass. And if I can calculate the percentage of this solution to be 20%, let's say the percentage composition, weight in weight percent of this solution is 20%. It means that, if it's 20%, weight in weight percent, 20, I can imply that the mass of the solute in 100 gram can be 20. So in 100 gram, assuming 100 gram of solution, 20% is H2SO4. That means 20 grams is H2SO4. Therefore, the mass of the solvent is 80 gram. I can as well use 1000 gram. Here will be 200, here will be 800. But my point is that the molarity of 100 gram solution is the same molarity for 1000 gram solution. So I'll just use 100 gram. I'll just say anytime I get percentage to be 20%. So from percentage, you can always get molarity. So for short, once you have percentage, what is molar? Once you have percentage composition of the solute, how do you get molarity? The particular percentage will be the mass of the solute. Then 100 minus the percentage will be the mass of the solvent. Simple. So like that, I've analyzed this question and I can do justice to it in seconds. In seconds, I'll put another one for clarity. So let's quickly just do justice to it. Now, the first thing is to get the percentage composition. So when you are asked to look for molality from molarity, the first thing you have to do is to calculate the percentage composition. Calculate the percentage composition. So calculate the percentage composition. So percentage composition is 10 times P times D. D is percentage composition. Remember weight in weight percent. Weight in weight percent, that's the most common one in stoichiometries of solutions. So there's weight in volume percent or weight in volume percentage. Yeah, or volume in volume percentage. So 10 all over molar mass. So all over molar mass W. So quickly, now let's input our value. Now, molarity is 1.55. So 1.55 molar equals to 10 times. We are looking for percentage. From percentage, you can then calculate for molality, percentage conversion of weight in weight percent. The density is 1.18. I already said when using this formula, your density should be in gram per milliliters or gram per cm cube, not gram per dm cube. So then um, what is the molar mass? Molar mass is 98. So the molar mass of H2SO4 is 98. So like this, I can make P subject of formula. Making P subject, I should have P is equal to 1.55 times 1.55 times 98 all over 10 multiplied with 1.18. So pardon, multiply with 1.18. So what should I have? So quickly using my calculator, I should say using my calculator, I should have 1.55 times 98 times 10 times 1, sorry, 1.55 times 98, that's divided by 10 divided by 1.18. I should have 12.87. So the percentage composition of H2SO4 in the solution is 12.87. That is step one in solving the question. Now, I already said that if your percentage of a solute is a given value like this, if the percentage of the solute is a given value like 12.18, it means that the mass of the solute in 100 grams should be 12.87. Therefore, what should be the mass of the solvent? As we will need that to calculate for molality. So the mass of the solvent should be 100 minus 12.87, pardon, 1200 minus 12.87, because there are two things in a solution, A and B. So A is H2SO4, B is the solvent, and the solvent is making 12.8, the solute, I mean H2SO4, is making 12.87 of this solution. It means that the solvent should make 100% minus 12.87. Yes, so I'll just assume 100 gram. I already explained that. So the mass of the solvent should be 100 minus 12.87. That should be 100 minus 12.87. That should be 87.3. 87.13. So that is the mass of the solvent. So quickly I can get molality. So what should be molality? So my molality should be as 87.13. My molality should therefore be, let me get molality. What should therefore be my molality? My molality should be, so molality, molality should be, remember it is mass over molar mass times 1000, or rather mass over molar mass is W, times 1000 over mass of solvent, big M. So what's the mass of the solute? 12.87 over the molar mass is 98 times 1000 over the mass of the solvent is 1000 over 87.13. Now, many of you will be asking, why is this one 12.87 and this is 87.13? I already said this is for 100 grams. We just assume that the solution has a mass of 100 grams. The molarity of 100 grams of a solution is the same molarity of 200 grams. In as much as the composition of the solution is not changing, just take a little amount of it. So if I prepare a bottle of Coke with 0.2 molar, I take just a drop of the Coke. The drop I took is also 0.2 molar. You get so the molarity does not change. Just assume 100 grams. Since it's a percentage, it is easier. So please take note, once you have a percentage of a solution, let's say the percentage composition of ACl is 40%, means that in 100 grams there's 40 grams of ACl, and the remaining part is a solvent or any other thing present. So that's how it is. So for molality, what should therefore be molality? So please, this is the simple trick of, it's one of my simple tricks. I have other simple tricks. It's one of the simple tricks I used to get molality from molarity. So I have molarity, that's also molality. So what therefore is molality? So molality is therefore going to be 12.87 times 1000, that's divided by 98, then divided by 87.13. So that should be 1.51 molar. 1.51 molar. So that is the answer. 1.51 molar. Very simple, easy peasy. Very easy but kind of tricky. So I'll try to solve another one now. So I'll quickly drop another one. This one will be more simpler. Another one. All right. I have our fourth example here. Our fourth example already. And it says that, let me come. So you see it. So it says that calculating molality, same question like the other one, just a little different, of a solution of 0.5 mole per dm cube, which is molarity of Na2CO3 with a density of 2 gram. And I saw this question somewhere online somewhere, and the person was trying to. So I saw this approach somewhere. So let me know that they solve it with this, but I saw this approach somewhere, and this question they try to use that molality is equal to molarity over density. Please, this is 100%, 2000% wrong. Why? Molality is mole per kilogram of solvent. Molarity is mole per dm cube of solution. Density is kilogram of solution. Oh, so the kilogram in the formula of density and the kilogram, and you should know that kilogram per dm cube is the same thing as gram per cm cube. The difference is 1000, 1000. So it's the same thing. Like it's like saying this is equals to 1000 gram makes up 1 all over 1000 cm cube. Okay, 1000 stroke 1000. So kilogram per dm cube, same thing as gram per cm cube. No gram per cm cube, same thing as gram per mil. So this kilogram here is for the solution. This kilogram here is for the solvent. So this formula is 100% wrong. As I said earlier, it is 2000% wrong. Very wrong. So you cannot solve it with this. So you apply my approach in the first the example 3 above. So my approach in the example 3 above goes like this. Very simple, easy peasy, easy peasy. Don't let it scare you. It's simple. So what did he say? The approach in example 3 says that first I have to get my percentage composition of this solid in the solution. So molarity is 10 times P times D all over molecular mass. So quickly. So let's quickly go. Molarity was given as 0.5. We'll just quickly impute. That's 0.5 mole per dm equals 0.5 molar. Then 10 times the percentage is what we're looking for. Times the density is 2 all over the molar mass of Na2CO3 is 106. So simple. Very simple. Very simple. Pardon me, let me get my calculating material. Okay. Therefore, I can make P subject of the formula. Can therefore make P subject of the formula. So making P subject of P is therefore equals to 0.5 times 106 all over all over um all over 10 times 2. Simple. Okay, this should be 4 times 106. So let's just do 0.5. Okay, 0.5 times 106. 3 divided by 10 divided by 2. So I have 2.65%. 2.65%. So the percentage composition of Na2CO3 in its solution is 2.65%. So with 2.65% or 2.65 weight in weight percent, I can get molality assuming a 100-gram solution. Beautiful. So what can therefore be molality now? Remember that molality, you can pause and look at the previous explanation. You can remember that molality is equal to mass of solute small over molar mass of solute times 1000 over mass of solvent. Quickly, what is therefore molality? Molality. Now, first of all, if the percentage composition is 2.65%, it therefore means that in 100 gram, the mass of this solute is 2.65, and the mass of the solvent, so the mass of the solvent, big letter M, is going to be 100 minus 2.65. Chikena, like my Nigerian brothers will say. Yeah, that's simple. So then what is molality? Molality is therefore equals to what's the mass? The mass is 2.65 in 100 gram. All over the molar mass is 106 times now times 1000 over 100 minus 2.65. That should be 97.35. 97.35. So what should I have? What should I have? So what therefore my molarity simple 2.65 times 1000 divided by 106. Okay, divided by 106 divided by 97.35. So that should be 0.25, 0.25 or 0.26. So the molarity is 0.26 mole per kg. If you don't call it 0.2 or you say or 0.26 small letter m of Na2CO3. This is the molality. This is the molality. Okay, so this is the molality. So this is how to calculate for this. We're looking at another example, simple example. So molality, you should not forget the formula for molality. In case the question comes like this, they give you mass of solute and they give you the mass of the solvent. Mass over the molar mass of the solute or the number of moles of the solute all over times 1000 all over the mass of the solvent in gram. Make sure the mass of the solvent should be in gram. So in gram, this is in gram, yes. So this is how to calculate for molality. I'll quickly move to calculations on normality. Calculations on normality. Quickly on normality. Let me take one for normality. All right. I have another question here that has to do with calculate the normality of 86 grams of H2SO4 in 0.5 cm cube of solution. All right, for normality of 86 gram of H2SO4 is in 500 cm cube of solution. Now, quickly, I already said when I was introducing this chapter that normality is equal to number of equivalents of solute, per volume of solution. Now, but how do I calculate for number of equivalents? Number of equivalents is simply mass over equivalent weight. I'm going to give this a short formula: mass over equivalent weight. Okay, then what is therefore equivalent weight? Equivalent weight is is molecular mass, molecular mass, or molar mass as the case may be, over number of reacting units, over the number of reacting units. Yes, over the number of reacting units. You can digest that, digest it. Now, in your mind now, how am I going to calculate for the number of reacting units? How am I going to get equivalent weight? They are quite simple, very, very simple. Let me do it with this long step and I give you the short method to use. So with this long step, I give you the short method to use. So quickly, now getting the reacting unit, for acids, there are number of reacting units, because this will be the first point of the first problem we will count out. So for acid, the number of reacting units is their basicity. So I have acids such as H2SO4. The number of reacting units, which is in our question, is 2. We have acids such as HNO3. The number of reacting units is 1 due to the number of replaceable hydrogen and the basicity. Also, you have acid like H3PO4. H3PO4, though it might have 3 hydrogen, but has a basicity of 3. Yeah, it has a colleague. I like to call it its colleague. That this has a basicity of 2, despite having 3 hydrogen, because of the stability of the monophosphate ion. So this is for acid. What about for base? for base. Base is the number of replaceable hydrogen ion or their acidity. So number of reacting unit for base, number of reacting unit for base is the number of OH that they have, or the number of replaceable OH. This is one okay, CaOH2. The number of replaceable hydrogen ion is 2. We have other base such as other elements such as reducing and oxidizing agents. So for oxidizing agents, I call them OA, oxidizing agents. The number of reacting units depends. So I have an oxidizing agent like KMNO4. It is a change in oxidation of Mn in its most common reaction. Most of the common reactions KMNO4 undergo, it changes oxidation number from from plus 7 to plus 2. So the change in oxidation number is 5. So the number of reacting units for KMNO4 is 5. Now, I have things like K2CrO207. So I'm just talking about common K2CrO207. So that's potassium dichromate. So K2CrO207 changes oxidation number from plus 6 to plus 3. So the central atom, which is chromium, usually changes oxidation number in its redox reaction from plus 6 to plus 7. So the number of reacting units for K2CrO207 is usually from plus 6 to plus 3. So the number of reacting units is the change in oxidation number, which is usually 3. So 6 to 3. So also for ammonia, you have things like ammonia. Ammonia in solution can form NH4OH. So the number of reacting units is going to be 1 for ammonia. The number of reacting units is going to be 1. Yeah, before I go on to solve this question, you can get questions like calculate the equivalent weight of ammonia. Calculate the equivalent weight of ammonia. You can get questions like that. Calculate the equivalent weight of ammonia. How do you then solve questions like this? How do you solve questions like this? Calculate the equivalent weight of ammonia. So how do you solve questions like this? To solve questions like this, let's say equivalent weight for ammonia. I told you equivalent weight, if you saw my previous formulas, so equivalent weight is equal to um, molecular mass or formula weight over number of reacting units. So this is as simple as this. So molecular mass or formula mass over number of reacting units. So for NH3, what is the equivalent weight for NH3? I told you the number of replaceable OH in solution. It's a base is 1. So the number of reacting units for ammonia is 1. So the formula weight for ammonia or the molecular mass is 17. So nitrogen is 14, H is 1. So what do we have? We have nitrogen plus 1 plus 1 plus 1, that's 17. So we have 17. So for the equivalent with equivalent. So for the equivalent with, pardon, for the equivalent with, uh, we have 17 all over 1. So the number of equivalent weight or the equivalent weight for ammonia is 17. So it's usually 17 gram per mole. That's also the unit. 17 gram per mole per unit. So that is the number of equivalents. That's how to get the equivalent weight for a solution or for a compound. So diving into normality, solving the question I dropped earlier, or solving this particular question in front of us is very dicey. Very dicey, but I have a shortcut for it. So let me just quickly try my normal way if I use my shortcut. So trying my normal way, I should have that. The first thing I should have to calculate for is equivalent weight. If you saw what I did earlier, you have to calculate for equivalent weight. So equivalent weight is going to be the formula mass of H2SO4, which is 98, as the molecular mass, the formula mass, which is 98, H is 1, S is 32, O is 16. So if you do 16 times 4 plus 32 plus 1, you get 98 as the molecular mass. All over the number of replaceable hydrogen ion is 2. So the number of reacting unit is 2. So 98 all over 2. I have my calculator here and I can get my equivalent weight to be Okay, 98 divided by 2, and that should be 49. So the equivalent weight is 49. 49. Then thereafter, I go to calculate for my number of equivalents. So my number of equivalents, if you watch my formula, is equal to the mass of the substance all over equivalent weight. All over equivalent weight. And if I do this, the mass given was 86. So I have 86 all over 49. So 86 all over 49. And the number of equivalents of H2SO4 in this solution should be 86 divided by 49, and I have 1.755. So I have 1.755 equivalents or per equivalent. Gram per equivalent. So quickly, I gotten the number of equivalents. Now remember, normality is number of equivalents per liter. So normality is number of equivalents per liter of solution, or number of equivalents over volume in solution, volume in liters. Okay, volume of solution in liters. So normality is equal to number of equivalents per volume of solution. So volume of solution, if there's a, and this volume should be in liters. If it's in milliliters, I normally add 1000 to the numerator. So I multiply numerator 1000. So I have my number of equivalents to be 1.755. Let me do that again. I just cleaned the figure. So I said it was 86 divided by 49. 1.755. So my normality is therefore equal to, and if you check, in 500 cm cube. So in 500 cm cube. So the volume is 500 cm cube. So the volume is 500 cm cube. So cm cube is the same thing as milliliters. So cm cube is the same thing as milliliters. So to convert 500 milliliters to liters, it's going to be 500 over 1000. So this 500 milliliters is the same thing as 0.5 liters. 0.5 liters. So number of equivalent is going to be um number of equivalent is going to be um um 1.755 over 0.5 liters. So, or if I don't want to put 0.5, I can say 1.755 times 1000 over 500, just to convert the 500 cm cube to liters. Just to convert my 500 cm cube to liters. Okay. So at the end of the day, so 1000. At the end of the day, at the end of the day, I'm going to have let me check. I'm going to have 1.755 divided 0.5. So I have 3.51. So my normality at the end of the day is going to be 3.51 equivalent per liters. Equivalent per liters. So this is the normality of the solution, 3.51. So it's very simple. To get normality is very simple. But let me give you a formula that you can use to save all this stress. I'll give you a direct formula to just solve normality. So the direct formula for normality would be, quickly take this, direct formula for normality, I call it my own shortcut, would be molarity times R. Molarity times R. What is R? R is equals to number of reacting units. Number of reacting units. So what is normality? Normality is equals to 1000 times mass, or let me just put it the normal way. Mass times 1000. Let me adjust. Simple adjustment. So this is normality. Normality is equals to mass times 1000 over molecular weight. over molecular weight of molecular mass, formula mass, W formula mass, molecular weight, times volume. Now, because of the 1000, the volume should be in cm cube or or or, or milliliters. So times R. So this formula, this is the sole general formula for normality. So you can take it down. So anytime you come across normality, this is how you solve it. Where R is number of reacting units. Where R is number of reacting units. So so we can impute and we have you can impute and we have normality to be. So what will be normality? On impute, normality will be we impute. So mass is 86, 86 times 1000. For H2SO for arrow is 2, number of reactants is 2. Molecular mass is 98 times 500. So when you impute like this, you get your normality to be very, very simple. So you observe that normality is very simple. So imputing, you should have 86 times 1000 times 2 divided by 98 divided by 500. So we're having 0.351. Okay, where is the mistake coming from? So 86 times 1000 times 2 divided by 98 dividing by 500. So we have 3.51. So 3.51 equivalent per liters. So these are to trash the concept of um normality. So that's simple. We can try other examples as often. So I'll quickly check the concept of mole fraction, the concept of mole fraction and mass percent, if possible. Concept of mole fraction and mass percent. One or two simple example. Now tell you how you can get molarity from mole fraction. Okay. You can get molarity from mole fraction. So one or two simple question. One or two simple question. Simple simple question. Okay. All right. Now this simple question is in front of us, and what do we do about this simple question? Um, Very simple. So it says calculate the mole fraction of 300 gram of glucose um, in its aqueous solution of 1000 grams. So the solution is 1000 gram. Aqueous means that it is in water. So therefore, that means we have the solution equals to glucose plus water. Solution equals to glucose plus water. Glucose is 300 gram. Water is therefore going to be 700 because the total is 1000 gram. So that's 1000 gram. So quickly, how do we work? So now, since the same mole fraction, we're going to get the number of moles of glucose. So glucose C is 12, H is 1, O is 16. So glucose is C6, H12, O6. This might be the only dicey work in the equation. So to get the number of mole of glucose is the molar mass, the mass over the molar mass. The mass of glucose in the solution is 300. So 300 over the molar mass is 180. We check 12 times 6 plus 12 times 1 plus 6 times 16. So 300 over 180. What do you have? So 300 over 180, you should have 300 divided 180. You have 1.67. So I have 1.67 moles. Okay, then what is the number of moles of water? Number of moles of water, because water is H2O. So water is H2O. So we have a mixture of glucose and water. Water is H2O. So how do you get the number of moles of water? So number of moles of water will therefore be equal to number of moles is going to be The molar mass of water is 18. So we have about 700 grams of water, which is solvent, over 18. So what do you get? 700 over 18. What do you get? 700 over 18. I should have 700 divide 18. I have 38.89 moles. 38.89 moles. So 1.67, 38.89 moles. So I need the mole fraction of glucose. So how do you get mole fraction? So simple. I want to place it here. So mole fraction should always be noted to be, so this is mole fraction. So mole fraction should be noted to be x. That's the symbol. Mole fraction is x. What I mean? We have x. Now for glucose, the mole fraction of glucose will be therefore the number of moles of glucose over the number of moles of the total things in the mixture, glucose and number of moles of water. So number of moles of glucose. So that will be the mole fraction of glucose. So mole fraction is usually the number of mole of a material by the total number of moles of the substances present in the mixture. So the mole fraction of glucose is this. So we have the number of moles to be of glucose to be 1.6. So number of mole of glucose is 1.67 over the number of moles of glucose again. There are only two things in the mixture, which is water and glucose. So which are water and glucose. So number of moles of water is 38.89. So having this, the mole fraction of glucose should therefore be um, um, 1.67 plus 38.89. And that should be 40.56. So, okay, 1.67 divide 40.56. Okay, that's mole fraction. If you do this, you will have 0.0411. Mole fraction usually have no units. So mole fraction, you can also be asked the mole fraction of water in this kind of question. It's very simple. So my point of call would be how to get molarity for mole fraction. That should be the dicey part. How to get molarity for mole fraction. So we do, yeah, a simple question to get polarity for mole fraction. It says calculate the molarity of a solution of NaCl with mole fraction of 0.1. Yes. Now, usually most NaCl solutions should be noted that most NaCl solutions are aqueous. So most of NaCl solutions are actually aqueous. So how do you get mole fraction from an aqueous solution? So how do you get molarity from an aqueous solution of NaCl with the mole fraction of NaCl 0.1? So first of all, the mole fraction of NaCl, the mole fraction of NaCl is equals to 0.1. Now, it means that the mole fraction of the solvent, which is most likely to be water, is actually 1 minus 0.1, which should be 0.9. So the mole fraction of a solvent in a mixture of its solute and the solvent is 1 minus the mole fraction of the solute. So as simple as that. So since we have the mole fraction of the solute, we assume that the total mole is 10. We assume, okay, let me just put it here. Assume total mole is 10. So if total mole is 10 and the total mole is 10 mole, yes, it's 10 mole. If total mole is 10 mole and the mole fraction of NaCl is 10, it means that the number of mole of NaCl, is going to be fractions like a percentage. The fraction is going to be 0.1 times 10, which is 1 mole. Then the mole of H2O will be 0.1 times, of H2, 0.9 times 10, which is 9 moles. So we get their various moles like that. So the molarity of 10 mole of solution with mole fraction of 0.1 is still the molarity of 100 mole of NaCl solution with mole fraction of 0. In as much as the mole fraction is constant, the molarity is constant. So we can just assume a given mole. So we can just assume a given mole and we solve. So first of all, having assumed that the mole is 1 and 9, so the mole can be 10 and 90. The mole can be, depending on your figure, the mole can still be 0.1, 0.9. So we'll just assume that the total mole is 1. The 0.1 of 1 is 0.1, 0.9 of 1 is 0. So the mole fraction of in as much as the mole fraction is constant, as I said before, the molarity is constant. So we should know that. So I haven't gotten that. I haven't gotten the mole. I've assumed the mole total mole is 10. So I want to try and get the molarity. So first of all, I need the mass of NaCl for that 10 mole. So for that 10 mole of the solution, the NaCl mass, remember, number of mole is equals to mass over molar mass. So the mass of NaCl should be needed in order to get molarity. Okay. Um, I might not really need the mass of NaCl because molarity says that molarity is number of mole over volume of solution. Yes, number of mole over volume of solution. So I don't really need the mole of NaCl. So the mole of NaCl, I will not need the mass of NaCl, pardon, I will need the mass of water in order for us to get the volume. So for water, the number of mole of water is mass over molar mass. The mass of water is unknown. Um, um, the mass over molar mass W. The molar mass of water is 18. So the number of mole of water is 9. So therefore, we can see that the mass is equals to 9 times 18. So mass of water is equals to 9 times 18. So getting the mass of water, I should have 9 times 18, which is 162. So the mass of water is therefore 162 grams in 10 moles. In 10 mole. So if it's 162 grams in 10 moles, I can now get molarity. Now, recall, it should be recalled that should be recall should be recalled that the density of water is 1 gram per milliliter. Now, what does that statement mean? It means that for every gram of water, statement means that for every gram of water, there is a single mil of water. Let me write this word so you see it. So this statement, okay, this statement means that for every gram of water, there's 1 mil of water. That means this 162 gram can be 162 mil of water. So having gotten this, so this can be for water. Remember, this is the mass of water. So let me just write it. So mass of water. Okay. So having gotten this, we can now assume that the volume of water is 162. And for solutions, in order to get the molarity, especially aqueous solutions in water, the the volume of water is most cases the volume of the solution. Now assume this: when you put a small amount of salt in water, does the volume actually change? The volume does not really appreciably change. It's just the volume just is increased by a tiny fraction. So usually the volume of water for aqueous solution usually the volume of is usually the volume of the solution. So it's like adding a 0.1 mole of NaCl, a very small amount of NaCl to 9 mole of water. The volume may not really change. So we can assume that the volume of water is equal to the volume of the solution. So if I should write it here, so volume of water, if you are following this my calculation, volume of water is equals to 162 mil from the mass because the density is 1 gram per mil. So since there's 162 gram of water, there's 162 mil of water. Using our molarity formula which says, if I should remember our molarity formula which says 1000 times mass of solute over molar mass, which is W, times volume of solution. It should be noted that these two are for solute, mass of solute, volume, molar mass of solute. So mass over molar mass is number of mole. I can rewrite this formula. Hope you're following. If you're not following, I'm just scroll back a little. It's simple, self-explanatory. So I can rewrite this formula and say, I can write this formula and say that molarity is equal to 1000 times number of moles of solute over volume. Now, the volume is in mil because of the 1000. So if yours was not 1000, the volume should have been in liters or dm cube. Here it is in milliliters. So, imputing our parameters, I have the number of mole of solute. The number of mole of solute is 1, so molarity is therefore equals to, what is molarity? Molarity is therefore equals to 1000 times the number of mole is 1 in 10, assume 10 mole. Then 162 is the volume of the solution, or volume of water. So in when solving for molarity, especially in aqueous solution, when the volume of the aqueous solution is not given, use the volume of water as the volume of the aqueous solution. So what therefore is our molarity? Our molarity would therefore be 1000 times 1 divided by 162. So that should be 6.17. 6.17. So our molarity is going to be 6.17 um, 3 molar or mole per dm cube. So I recall, what did I do? What did I do again? So I assume that the total mole is 10. I can assume that the total mole is 1. Or if you are confused, just assume that since the mole fraction of NaCl is 0.1, just take the mole of NaCl to be 0.1 and take the mole of the solvent as 0.9. You can also work with that. Then what you do is that you do, because it's NaCl, the solution usually in water. So this question can be of an aqueous solution, or this question is supposedly to be of an